In this video, we're going to talk about aromaticity and some of the requirements that are needed for aromaticity or for a molecule to be aromatic. So if a molecule is going to be aromatic, it must meet all of the following criteria that we are going to talk about. Note it's important that it must meet every single one, right? It can't just be a few, it has to be all or none. So the first thing is that a molecule, in order to be aromatic, must be cyclic, right? So it must be in a ring. The next rule is that it must be planar. So that means that it must be sp2 hybridized at every carbon or atom that is there. And every atom, therefore, since it would be sp2 hybridized, must have a p orbital. And those p orbitals all need to be in conjugation. Finally, the last step or last rule here is that it must contain what is called Huckel's rule, which is an uninterrupted system, i.e. conjugated, of 4n plus 2 pi electrons, right? And they all must be cyclic, right? And we'll go into more detail about what this 4n plus 2 pi electrons really means. We'll talk about that momentarily. Again, the 4n plus 2 is something that comes from what we call Huckel's rule or Huckel's rule. And this basically is a set of electrons that must be within a pi system where everything is conjugated, and where n, when you solve for n, must be an integer of some sort. So in other words, n needs to be a whole number, like 0, 1, 2, 3, so on and so forth. So if you add up the number of pi electrons and you end up with something that does not fit the 4n plus 2, what do you do? In particular, what do you do if all of the conditions are met except for Huckel's rule? Well, in this case, what we have are compounds that are referred to as anti-aromatic. These compounds are cyclic, they're planar, and they're conjugated. However, they exhibit 4n pi electrons. They don't fit Huckel's rule, and so therefore they're not aromatic, they are anti-aromatic. Now, finally, if you're looking at this and you see a break in conjugation, one of the big things you're looking for is there an sp3 carbon hanging around in there? Then what you'll notice is that this is now going to be considered to be non-aromatic. So let's do some examples. So here are some compounds that we have, and we're just going to go through and look. And the first thing, on the one on the left, I see that there is a sp3 carbon that is hanging out right there. So what that tells me is that even though this compound is cyclic, it's not conjugated all the way through. Even though the two double bonds are in conjugation, we have a break in the conjugation, and therefore this is going to be non-aromatic. Now we can look at the next one over in the middle, in the top middle, and we see that we have something that is completely conjugated, right? Everything is planar. The carbocation is sp2 and has a vacant p orbital. It's all cyclic, so it fits all the rules except for we have 4n pi electrons. You see each double bond has 2 electrons, so that gives us 4. Therefore, this compound is anti-aromatic. Now, the one on the top right, we see that we have something that is cyclic, we have everything that is conjugated together, and it turns out that that lone pair is actually pushed into a p orbital. So it may look at first like we only have 4 pi electrons, right? But what you see is that this lone pair actually adds to the electrons that allows this carbon to rehybridize, and it is set into a system that has 4 pi electrons, or 6 pi electrons, and therefore now this carbon is sp2 with the p orbital, the lone pair is in the p orbital, and this guy is now going to be classified as aromatic. So again, just to refresh, this lone pair is pushed into a p orbital due to the rehybridization for stability, and therefore we have 6 pi electrons, and this is now aromatic. If we go to the bottom left, what we see is, of course, an sp3 carbon, so this one is now easy. This one is no longer anything that's aromatic. We have non-aromatic there. We have a break in our conjugation at this point. And if we move into the next guy over, what you see is we have 6 pi electrons all the way around. The carbon at the top is sp2 hybridized, and that plus charge is in a vacant p orbital, and this adds to some stability. So what you can see is that all these p orbitals now, as I attempt to draw them in, are all sort of full of electrons, right? And so we have all of our electrons in conjugation, and this tells us that now we have something that is indeed aromatic. Since we have 6 pi electrons, it's cyclic, it's flat or planar, and everything is sp2 hybridized. We have all carbons with the p orbital. Therefore, this compound is aromatic. Now, if we move to the one on the right, what you can see is that we actually have 8 pi electrons in this case. And so very easily you can see that if you set this equal to 4n plus 2, you end up something that doesn't give you a whole integer, and so this gives you instead a number of n equals to 3 halves. So this one is anti-aromatic. This fits, so if you solve for 4n pi electrons, this fits that rule, and so this gives you something that is anti-aromatic. Now, one of the things that is important to note about aromaticity is that we have to include heteroatoms. So heteroatoms or heterocycles, what do we do those or call those? Well, basically anything that has something other than carbon. So here you can see a bunch of examples. We have nitrogens, here we have oxygen, we have sulfur. And so again, we want to remember that we still have the same set of rules. We have something that is cyclic, something that is planar with everything having a p orbital, and then we also have the requirement of 4n plus 2 pi electrons that we have here. All right, so let's look at the first one, pyridine here. What we can see is that we, of course, have something that fits all of the rules. It's cyclic, right? Everything, if you notice, around is sp2 hybridized. The nitrogen is as well. And we have 6 pi electrons. And the lone pair in the nitrogen is actually in an sp2 orbital in this case. Right, so it's kind of hanging out there, and we'll talk more about that in just a little bit later. So we can see that we have 6 pi electrons. This fits very nicely with Huckel's rule, and so here we have something that is indeed aromatic. Let's move over to Parole, and we see something that might be what you are considering an odd case. Okay, so I've got these two double bonds that both contain 2 electrons each, so that gives me 4 pi electrons there. So how many do I have? Well, right now with the double bonds, I have 4 that are in the ring with themselves, but we have a lone pair on the nitrogen, and it turns out that this lone pair is within a p orbital. So this nitrogen, in a sense, rehybridizes itself into an sp2 atom, and therefore these lone pairs are in a p orbital. These lone pairs now, since they're in the p orbital, contribute to the overall stability or aromaticity of the system. So therefore, this compound is now aromatic. This gives us a total of 6 pi electrons within the system. We can move over to furan down at the bottom left, and we can see we have something kind of similar, right? Oxygen has 2 lone pairs, and one of those lone pairs that we have here is actually going to be put into a p orbital, right? So it's going to allow this oxygen to, in a sense, rehybridize, push those lone pairs into a p orbital, and this will allow it to gain the stability of having an aromatic system and gives us 6 pi electrons. So if I can just kind of easily or briefly draw this little schematic, what you see is we have our p orbital, we have the lone pair from there, and then we have the other lone pair. It's important to note that the other lone pair is at a 90-degree angle almost to the pi system. It's in an sp2 orbital. The one lone pair there on top is in a p orbital, and that contributes to the overall pi system there. Same thing for sulfur, right? We have 2 electrons that are on there, right? So we have essentially the same deal. We have 2 lone pairs. One lone pair is here. It is in the p orbital, and the other lone pair is in an sp2 orbital. And so just like with oxygen, this sulfur is allowed to push its lone pairs into the pi system, and so now this gives us an sp2 sulfur here with a p orbital, and this gives us a total of 6 pi electrons, which makes it aromatic. Now, one thing that this has or can lead us to is notice that we're making some changes here, some things that you may not see. And I'm just going to briefly draw sort of another schematic here with all of the p orbitals that we have for this thiophene molecule. And you can see that these two guys are together. We have the p orbital that has the lone pair that is right in there. Notice everything is in conjugation, and then you see there the lone pair and the sp2 orbital at the bottom, right? So everything is conjugated here, and this allows this compound to be aromatic. Now, back to my point, this also has an important role when we talk about the basicity of certain nitrogens. So which nitrogens of these two compounds, pyridine and pyrrole, is more basic? We can solve this problem by looking at where those lone pairs reside. And we already know the answer. We know that the nitrogen here has an sp2 orbital that is holding the lone pair. So if we draw this out, one of the things that we see here, if I put nitrogen there at the end, right, we have nitrogen that already contains a p orbital that is within the system itself. And then the lone pair on the nitrogen is not going to be part of this. Notice that it's already sp2 hybridized. The lone pair is going to be pushed to an sp2 orbital there on the side. This is exactly something that is perpendicular to the pi system that we see. Now, since this lone pair is perpendicular to the pi system, right, it is not involved in maintaining the aromaticity. Therefore, these lone pairs are actually available for some bonding. So these lone pairs are actually basic. Now let's look at pyrrole on the other hand. Notice that pyrrole, remember, it needed to put those 2 lone pairs into a p orbital so that we could have something that is aromatic. Since those lone pairs are not in an sp2 orbital, but they are in a p orbital and part of the aromatic system, or basically we can say the pi system, those lone pairs are in a sense tied up. They're stuck being part of the aromatic system, and therefore they are not available for use as a base. If they were to be used as a base, then you would have a very unstable system. So therefore, this nitrogen is not basic. The lone pair is tied up into the aromatic system.